Now we're going to go on to fluctuating targets and then constant false alarm rate thresholding, adaptive thresholding. Okay, now to fluctuating targets. To let you know that targets really indeed do fluctuate and they're not like spheres, we show here on the left the cross-section, RCS, of a B-26, a World War II bomber at S-band, 3 gigahertz. And each of these decades, these circular circles represents 5 dB of cross-section. It's a little bit non-linear, but you can see that from aspect angle to aspect angle, there's a significant amount of fluctuation, and broadside, the cross-section is higher. And this is typical for a complex target, and by complex, there are a very large number of scatterers, and they're all competing constructively. So we have a lot of different scatterers that make up the target, and the amplitude of the target's going to vary a lot from pulse to pulse. And as you change the aspect angle, small changes in aspect angle as the target moves, and it's a little bit time later, can cause, when you have a large number of independent scatterers like this, they can interfere constructively and destructively and give you this kind of a pattern of cross-section change. So what we want to do is develop into our ability to calculate probability detection versus probability of false alarm and signal-to-noise ratio, this effect. And small aspect angle changes or frequency diversity, that is changing from pulse to pulse or scan to scan, can cause this effect, can cause the different constructive and destructive interference. Now the fluctuation models that we're going to talk about are used so that we can more accurately predict the detection statistics. But you can imagine, with so many scatterers on this target, it's a very hard thing to analytically calculate exactly what the cross-section of this kind of an object is. And also, as we look ahead, many modern aircraft or small single-engine aircraft like Piper Cherokees, while they're somewhat complex, aren't nearly as complex as this. And military aircraft, such as jet fighters, don't have, they have jet engines, relatively smooth surfaces, and far fewer different numbers. Although they have quite a number, they have a lot fewer scattering centers. And so that's going to take this into account. In the area of objects in space, spheres and cylinders, they have very different fluctuation statistics than a complex aircraft. Just imagine the first Sputnik. It was a sphere with 4 long antennae coming out of it. And so that was a big sphere. Or you can imagine a cone. We all think of nose cones from missiles. The staging in a rocket would be a cylinder and an engine in the back and a front face that could be a cone. They're relatively simple relative to this, but their detection statistics depend on the physical nature of the target and how the cross-section all comes together with the adding of the scattered electromagnetic field from each of the different scatterers, taking into account the phase differences caused by the difference in location of one phase scatterer on the object from another. Now first let's look at the swirling target models. And I put down just for, there's no physical significance to my putting an aircraft down here and saying that the largest scatter is these 6 or 7 or 8. It's just a generic object that I put down. But I want to use it to metaphorically show you the mathematics of the different models, the swirling 1, 2, 3, and 4, and their algebraic form. And first we're going to look at how the radar cross-section fluctuates for swirling 1 and 2 targets and swirling 3 and 4 targets. For a swirling 1 and 2 target, the probability model for the cross-section is an exponential, and that is a subset of the chi-squared probability distribution with 2 degrees of freedom. And it can be viewed empirically as what you get. You get this kind of a distribution if you had a large number of single scatterers, all of about equal amplitude. And the next model is where you have one scatterer that's much larger than the others, and it's roughly equal in size to the sum of the other cross-sections, but they're at different places. And that's the chi-squared 4 degree of freedom model, and it has this functional form. And that's in cross-section. Remember, those are power units. And sigma bar is the average cross-section in meters squared. Okay? Now, whether it's swirling 1 or swirling 2 depends on the fluctuations. We call them slow or fast. Now, just think of that air traffic control radar. It's going to be banging out pulses at approximately 1 kilohertz. Boom, 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 boom. And then it's going to, 4.7 seconds later, come back and hit it with another bunch of pulses. And what one would need to do was to look at the target and see whether empirically the targets were correlated within that 10 pulses, but uncorrelated from scan to scan, and then you'd use the swirling 1 model. If you have fast fluctuations, and they're independent from pulse to pulse, then you'd use the swirling 2 model. And the same thing analytical goes with the swirling 3 and 4 model when putting this probability distribution in for the target in terms of its voltage. Now when we look at the voltage, the amplitude, we get these models. The amplitude model, that is the voltage, is a Rayleigh distribution, and it has this form, where A is the voltage, the amplitude. And that's A times e to the minus A squared over sigma. And the swirling 3/4 distribution is called a central Rayleigh, with 4 degrees of freedom, and it has an A cubed with the same exponential. So these are the factors that would go in as the probability distributions of amplitude, just like we had a Gaussian noise come in for the which turned into Rayleigh again in the amplitude domain. When we were talking about noise, here we're talking about the target. Now, when we look at detection statistics of targets or noise, there are a lot of physical targets which don't obey these models, because I said there's no real super underlying physical nature where you can say, when you look at a target, you say, well, that's going to be this distribution or that. And so, and there's only one independent parameter you can pick, the mean cross-section of the swirling 1 or swirling 2 targets. And whether, from the amplitude point of view, there's only one parameter you can pick when you pick the model 1 and 2 or 3 and 4. And that is the mean of the cross-section. But there are other targets or noise entities that fluctuate differently than the swirling targets. They have longer tails physically. And there are two kinds of models that have been used greatly for both clutter and noise, where you have long tails. Really three. I believe it was Walt Weinstock brought to net. You first used the chi-square distribution in showing, but then later in the 70s and 80s, the log normal distribution was used in fitting the data. And then lately the Weibull distribution, which is another. These are all two parameter distributions. These two are that have long tails, and more than one parameter is needed sometimes to describe the distribution. And for the log normal distribution, it's the ratio of the mean to the median. For a Gaussian, the mean and the median are the same. For these distributions, there's a long tail of the upper amplitudes, and there are a lot of different things. There's actually been a book written on the log normal distribution. It's, as I pull out weird known artifacts, a corn distribution in the United States, the overall corn distribution fluctuates log normally. Don't ask me why. Some years it's a very, very good crop. But it's a much better crop, and it gives that tail to the distribution. Now, these different distributions are used under many different cases. With ground clutter, particularly with the very long and voluminous work that Barry Billingsley did over decades, the Weibull distribution is used to characterize ground clutter. And in his book that will be referenced when we talk about clutter, he uses the Weibull distribution. C clutter, which is background, can be characterized by a log normal distribution quite nicely. Jerry Trunk at NRL spotted that years ago. HF noise is log normally distributed. Birds, if you think of a bird as a background or a target, you may or may not want to see. If you're a radar ornithologist, you want to see it. If you're an air traffic control operator, you don't. But birds are like an Ehrenmeyer flask that fluctuates. And that kind of a semi-cylinder with a cylinder on the end with like a nose cone, the thin cylinder, fluctuating, that fluctuates log normally, as well as rotating cylinders, certain spacecraft, and other objects. So that there are lots of different times when both clutter and target can have these long tails of distributions, and many calculations have been done. Not just for the steady targets and the swirling target. The steady target's either called a Markham target, swirling class 0, or a steady target. Markham did these first calculations, and Peter Swirling did them for these classes of fluctuations. Then these calculations have been calculated by many different people. The chi-squared targets in Gaussian noise, Heidbreder and Mitchell, I believe at the Aerospace Corporation, calculated log normal targets in Gaussian noise. Jerry Trunk calculated, I believe it was steady targets and log normal noise. Log normal targets and log normal noise. I did that calculation probably 30 years ago. And Weibull targets and Gaussian noise, I'm sure, has been calculated. But there are a plethora of those receiver operational curves. And the main point, though, is find out how your target and your noise fluctuate. Most of the time, if it's a target that you can beat down with signal processing, you want to beat it down to to Gaussian noise and then deal with it. You can't deal with the target fluctuations except to change frequency. But most of the time you're going to be dealing with Gaussian noise. Okay, now let's just look at what these actually look like to the eye. A non-fluctuating target, it's just constant. A swirling class 1 or 2 have high fluctuations. The fluctuation rate is quite high. And the swirling 3 and 4, the fluctuations are medium. And here's the sample number. And the whole time, the thing you want to worry about, whether it's 1, 2, or 3, or 4, is how often, how quickly you make the next sample. Whether these are 100 samples, or you're taking a sample at 0, 20, 40, 60, 80, 100. Right? You're taking it 1, 2, 3, 4, 5, 6, 7, 8, 9. That will go to determine whether you're dealing with swirling class 1 or the 2, or the 3 or the 4. Whether the fluctuations are fast or medium. This is dealing with the size of the fluctuations. So we've got our two hypotheses. Here we have the target, which is a complex signal. And for a Rayleigh amplitude of the target, we can actually calculate the probability of detection as a function of PFA, where psi bar is the average per pulse signal to noise ratio. This calculation is relatively straightforward and can be done. The PFA is just the exponential minus to the minus threshold divided by the variance of the noise squared, and the probability of detection is just this integral, and the probability of detection is just that quantity. When we plug in the PFA, and here we get this quantity, so that we can